A is for atom. That's right. A is for atom, because atoms are the basic building blocks of all matter. Atoms are like the letters in the alphabet of the universe. So look what happens when we combine these letters. We get words. Atoms are like letters, and molecules are like words in our universal alphabet. All matter is made of atoms and molecules.
Hey, science guy.
Huh?
Even a banana cream pie?
Oh yeah, even a banana cream pie.
Atoms! Atoms are everywhere! I'm surrounded by atoms!
Hello, friends. I am an atom. Yes, an atom. Can you see me? Oh yes, I know you can see me on your screen, but I am just an imaginary picture of an atom. Real atoms are too tiny. You can only see them under a very special microscope. Actually, this big microscope can be called a machine. Okay, now you know that we're so tiny that we can only be seen with machines. Now I have a question for you. Do you know the meaning of your name? Very good if you know it. If you don't know, ask your parents. But I also know the meaning of my name. It means that which can't be cut, that which is uncuttable. Actually, it's a Greek word, which means it is indivisible, which means it can't be divided further or can't be cut further. In the center of an atom, there is the nucleus. It is made up of even smaller parts. These are called protons and neutrons. Each of these protons carries a positive electrical charge. The neutrons are equally as heavy as protons, but don't carry any electrical charge. So, the nucleus of an atom is positively charged due to protons. Now, electrons are outside the nucleus. They are orbiting around the nucleus. The electrons carry a negative charge. The total negative charge of electrons is equal to the positive charge of the nucleus. So in total, an atom is neutral. The positive charge of the protons is neutralized by the negative charge of the electrons. So it is like +1 is neutralized by -1, and overall charge of an atom becomes 0. The electrons are moving outside the nucleus at a very high speed. Can they run away from the nucleus? No, they can't run away. Every atom has the same number of protons, electrons, and neutrons. So there is an attraction between equally strong negative and positive charges. Due to this attraction, electrons can't run away, as positively charged protons keep them pulled towards them.
Do you know what an atom is?
Nope.
Have you ever seen one?
Nope.
That's right. You have never seen one, but you have seen billions. You are made up of tiny little parts called atoms. One atom is too small to see, but if you look at yourself in the mirror, you can see billions and billions of atoms. It's a small world.
Indeed.
So everything is made of atoms. Your house, your dog, your cat, mom, dad, and all your friends are all made of atoms. The sun, the moon, and all the stars are all made of atoms.
Take a look at this. It's our proper proportion giant atom model of science. Now, this part isn't very giant. That's because it's just the nucleus, the middle of an atom. Now, in here are two kinds of particles, protons and neutrons. No one knows what they would really look like. The protons have a positive electrical charge, like a spark, and the neutrons have no charge. They're neutral. They just hang out in the nucleus. Now, buzzing around the outside of the nucleus are very small particles called electrons. Maybe you've heard of them. In fact, the flow of electrons from one atom to another is called electricity.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to talk about the electric force of nature known as lightning. Lightning is the flash of light produced by the natural discharge of a large amount of static electricity. This discharge is sometimes called a strike. Lightning is very common according to fulminologists, the scientists who study it. Lightning strikes somewhere in the world between 40 and 50 times a second. Yet, as common as lightning is, scientists aren't entirely sure what causes it. We do know that during some storms, clouds develop areas of positive charge and negative charge due to the movement of ice and water droplets within them. Negatively charged areas form at the bottom of clouds, and positively charged ones form at the top. As the strength of the negative charge at the bottom of the cloud increases, it begins to repel negatively charged particles on the ground's surface, causing the ground to accumulate a net positive charge. When the difference between the cloud and the ground overcomes the insulating effect of the air between them, the charge coalesces into a bolt of lightning that strikes the ground. This is called cloud-to-ground lightning.
When lightning strikes, giant sparks of static electricity tear through the atmosphere at 100 million kilometers an hour. Up to 1 billion volts rip the air apart. In that instant, the current creates light waves, and we see a brilliant bolt of light race across the sky. The air inside heats up to almost 28,000 degrees Celsius. It expands so rapidly that it explodes, and we hear a deafening clap of thunder. It all happens in less than the blink of an eye, up to 8 million times every day. This is one of nature's most frequent and best observed phenomena, but it's also one of the least understood. Somewhere inside this cloud, lightning is preparing to strike. Understanding how has puzzled scientists for centuries, but they think the cloud acts as a giant electrical generator. Inside the cloud, tiny water droplets rise up, freeze, and fall back down as ice. On the way, they rub against each other, and electrically charged particles transfer from one to the other. The water and ice particles that were previously neutral are now positively or negatively charged. The negative particles sink to the bottom of the cloud, while the positive rise to the top, separating the positive and negative charges. When they reunite, lightning will strike.
Because electricity moves over the path of least resistance, lightning tends to strike tall objects. For safety, we sometimes equip buildings with lightning rods, which safely conduct lightning's electricity down into the earth through a wire.
Hi, I'm Wesley Benson with more science news you can use.
Ow! That doorknob just zapped me. Why?
You got zapped because of static electricity. Let's figure it out. See, all matter is composed of atoms. Atoms usually have an equal number of positive and negative charges, protons and electrons. Atoms can gain or lose electrons when two different materials, like you and the doorknob, contact each other. As you walk across the carpet, you develop a negative charge as electrons move from the carpet to you. This charge is known as static electricity. When you went to open the door, the electrons jumped from you to the doorknob. That caused an electrical spark. Shocking, isn't it?
Is there some way I can avoid getting shocked?
Easy. Make your brother open the door for you. Until next time, I'm Wesley Benson with more science news you can use.
Bill Nye the Science Guy.
Now suppose we want to make a big static electrical charge. Well, we could use something like this. This is called a Van de Graaff generator. It's named after Robert Van de Graaff. So here's what happens. Electrical charges are deposited on this rubber belt. The rubber belt turns and redeposits the electrical charges up here on this metal ball. Now, since this next part of the demonstration rocks, I'm going to put on my rocker wig of science. Yeah! Now, start the rubber belt turning. Electrical charges are being deposited on the metal ball. They're running through my arm and being deposited in me. And look, it's building up in my rocker wig of science. See, since these charges are all the same, they're not attracting. No, they're repelling. They're pushing apart. So they're pushing the hairs of my rocker wig apart. Now, if I could find a way to get these electrical charges off of me back into some other parts of the room, the hairs wouldn't repel each other. There wouldn't be a static electrical charge. No, the charge would jump. Let's try it. Watch what happens when I bring this ball near this ball. See the spark? The charges jumped. The static electrical charges aren't static. No, they jumped. Static electricity. It rocks. See that? It sparked.
Bill Nye the Science Guy.